Hello, SPH4C. It's Mr. LaRusso here. We're going to do a quick little lesson on simple machines. And before we can talk about simple machines, we have to define what a machine is to begin with in the first place. For example, a machine is any device that helps us perform a task, and they're designed to achieve at least one of the five main functions. One is to change energy from one form to another. So example, like a windmill, where we take wind and we convert it to electricity. Or you take chemical energy and convert it into motion. So for example, when you put gas in your car, the chemical energy in the gas is designed to run the engine, which then in turn turns the wheels and you drive away. Another example would be a hydroelectric dam, where we actually block the water and we have the water turn turbines to generate electricity. Or back before the days of electricity, we used water to run mills. That's why a lot of sawmills and a lot of farms, especially in the Netherlands, where they used windmills in the Netherlands to do their farming, but there was also places, especially in North America, where we had lots of water and lots of running rivers, and we used those to do a lot of the work for us. The other purpose would be to transfer energy. So, for example, you use a machine to use one type of motion to create another type of motion. Bicycles use levers and gears to make our circular motion with our feet turn into translational motion of our bike. So we can actually move from point A to point B without actually having to do the walking. That's a means of using a simpler way of us to biomechanically do something to turn it into something useful. Change of direction of force. So, for example, you need to lift up a heavy garage door. Well, lifting up a heavy garage door by kneeling down and physically lifting it up is a lot more difficult than, say, pulling a cable down or a chain pull. So a lot of times we design machines to help us actually simplify a task. Another example is to change the magnitude of a force. So removing a tire by using a wrench. You are likely not going to be very successful by trying to unscrew a bolt by using your hand. However, if you use a lever, we can actually make that job significantly easier and, to be honest, possible. And then another example would be to change the distance or the speed. So this is what a gear system works. So on a bicycle, for example, bikes are actually designed as speed amplifiers as opposed to effort amplifiers. So on a bicycle, our goal is to actually increase our overall speed. Think about walking or running. When you're walking or running, you have a limit in terms of how quickly you can go. But on a bicycle, if you adjust the gears and if you're on relatively flat terrain, your feet are rotating relatively slowly, but the bike is moving significantly faster. So gear systems on a bicycle, for example, are speed multipliers. Whereas if you're trying to lift something very heavy, so for example, in auto shops before the advent of electric and hydraulic lifts, these were often used with pulley systems where mechanics would actually have to lift entire engines by using pull chains and pulleys. So there's an example of where you can actually use a machine to make the job easier or even physically possible to do. Levers are another example. So let's talk about what sort of classifications we do have for simple machines. So a simple machine is a device that performs one simple task, and they are broken into the following categories. So we have the lever family. So the lever family includes just plain old levers. So a wheelbarrow, for example, even a door handle is an example of a lever. Pulleys, wheels, axles, and gears. These are all under the lever family. And then you have something called the inclined plane family. So an inclined plane is just another word for a ramp. So a ramp is an example, a wedge, a screw, stairs. These are all examples of inclined planes. So levers are just rigid bars that rotate about a point called a fulcrum. So here's our fulcrum right there. That's what we mean by that. And the fulcrum is just another way of saying a point of rotation. So this object here, that's your load. Now, if you notice something, the distance from here to here versus the distance from here to here. So our job, what we're trying to do, is we're trying to take this heavy object and we're trying to lift it up. We use a lever to help us out. And with the lever, the effort that we apply is over here. In this case, this is known as a first class lever, and it's all about the ratio of how long the load distance is versus the effort distance. So let's zoom in here. So from here to here, that's the distance of the load. From here to here, that is called the effort distance, or the distance of the effort. So anyone who's had any experience working with a lever, just even opening a door, you know that the longer the lever is, the easier the job is. Well, in fact, it actually has to do with the ratio of these numbers, right? The bigger this one is, the easier the job is, right? So this one, we try to make it smaller. And that makes the effort much easier to do in this case when we have this particular ratio. Now, that's not the only type of lever system that we have. We have also something called a second class lever. In a second class lever, our point of rotation, or our fulcrum, is this point right here. The weight of our load is this distance right here. So this would be our DE. And our effort force would be somewhere here. If you look carefully, you should recognize things like torque here, because this is all about rotation, which is associated with torque. So the advantage of this particular case here is that we can take a very heavy load and we can lift it with relatively low amounts of effort. And of course, the wheel also helps us move the load across by reducing the amount of friction. It's easier to move things across. So as opposed to actually physically trying to carry this thing with your arms, you actually use this second class lever to do the job. And again, the ratio of this effort versus, oops, and I miswrote that. Sorry, the blue is the distance of the load. My bad. So the distance of the load compared to the distance of the effort. So the larger the effort distance, the easier the job. The shorter the effort distance, the harder the job is. Now let's take a look at a third class lever. Now, in these two examples up here, the first class and the second class lever, these are all about making the job easier to do, physically easier to do. But sometimes what we're trying to accomplish is not produce less effort, but actually cover more ground. And this is what we call the third class lever. All right, so here, the fulcrum is this little point right here. Now, it's kind of misleading on the diagram a little bit here. But when you actually twist your, they have the fulcrum all the way at the end. Oh no, actually, I guess it would be considered at the end. Yeah, depending on how you rotate it. So if the fulcrum is there, the distance from here to here, this is the distance of your load, where your effort distance is this shorter one right here. So in this case, this force effort is actually bigger than the force of the load. So why would you want a situation like this? Well, here's an example where we actually want this thing to move a larger distance. See, for example, you only want to rotate your arm a little bit, but you want to bring this entire load, specifically the fish, from deep in the water out of the surface. And that's where using something like a fishing rod is helpful, that we actually can have the load that we're trying to get cover a much larger distance than normally we would have to do it. Otherwise, we would physically have to move our body huge amounts of distances just to bring this out. So sometimes a lever system, we're not looking for like physical effort to be less. We're looking to have the load move a larger distance. Another example, a crane. This is another example of a third class lever. So the human body has actually evolved to be to exploit these types of levers as well. And our arm is actually an example of a third class lever. So let's take a look. So here, where our elbow is, this is where our effort exists. My apologies, that's where the point of rotation, that's where our arm rotates, is about our elbow. The load arm is represented by this distance here. So this is the distance of the load, and this represents the force of the load. And our effort comes from our muscles right here. Distance of the effort and the force of our effort. Now, of course, not only do we have a lever here, but we also have at this end here too. And that's why when you extend your arms out and try to lift something very heavy, it becomes very difficult. It's why we tend to bring our shoulders and our arms close to our side when we lift something up, because the effort is a lot easier. Anyone who's done has done a workout in the gym and has had to do flies understands how harder it is when you stretch your arms out. Okay, so let's take a look at pulleys next. So here's a rope and a pulley system. Now in this particular setup here with a single pulley, there is actually no mechanical advantage. And the reason why, here is our point of rotation, and the distance of our load is equal to the radius, and the effort of the load is pointing down like this. So that's the distance of our load, and this is the effort of our load. This is the distance of our effort, and this is the force of our effort. So in this particular case, the job isn't easier in terms of the amount of force we have to apply, but it is physically easier for our bodies to do this. So for example, when you want to lift something up by just leaning over and having to grab this and lift it straight up, not only do you have to lift the load up, but you also have to physically lift your body up. And that takes effort. So your body has mass. So you need to lift the object in question plus your body. Whereas when you're using a pulley like this, actually your own physical weight helps with the job. So when you pull down something, you're actually working with gravity. So your arms are being weighed down by gravity. Your body's being weighed down by gravity. So by simply pulling down on this rope, you're actually having gravity work with you by using your own weight to help pull this object up. So even a single pulley does make the job easier for us, not because we have to apply less force on the load. We actually just have to apply less force overall because we don't have to worry about lifting up our bodies. Here, we can actually let our bodies just passively do the work for us. In this particular configuration, this one we actually do have a mechanical advantage. And let's take a look. Now here, in this case, this is the fulcrum. And the reason why this is that when we lift here, the whole pulley itself is actually going to slide up when we do this. So that is the distance of our load, and this is the force of the load, so how much weight it has. This is the distance of our effort, and this is our effort force, or the force of our effort. And as it turns out, this job requires half the force of how much this weighs. So let's say this object had a weight of 10 newtons. Our effort force would actually only be 5 newtons. And now here's the reason why. Because when you look at it from a free body diagram point of view, we're pulling up on one side of the rope, but the ceiling is actually doing the other half of the work. So drawing the free body diagram, so our force of the load is 10 newtons, but since there are two up strings, the tension on the left string and the tension on the right string have to add up to 10 newtons. So this one would be 5, and this one would be 5 as well, for a total of 10. So the more up strings we have with a pulley, the easier the job becomes. But there is a cost to that. So when we do this, we have to actually pull double the amount of string in order to lift this up a certain distance. So say, for example, we want to lift this up by a total of 1 meter. Here, we'd have to pull 2 meters worth of string to bring this up. And that concept might be a bit confusing for some folks. So let me give you an idea, and let me help draw it out for you. All right, so let's say this is our pulley. So that's the string on the left, and here's the string on the right. So let's say we want this thing to move up by the equivalent of this distance here. So we want to move it up by the length of this disc. Well, in order to do that, we have to shorten both sides by this amount. So on the left string, we have to remove this amount of string, and on the right hand side, we have to remove the exact same amount. So as you can see, if we want our load to move up by this amount, we have to remove double the amount of string from that rope. So if you're pulling on this side, if we want to raise this by 1 meter, you have to pull 2 meters of rope in order to make it move. So in this case, the job is physically easier, but we have more rope to pull. And that's how we get mechanical advantage. We have to compromise. If you want easier effort, then that means you got to go further. So a prime example, that's how ramps work. So if you have to climb a steep hill, it takes a lot of effort, but you don't have to travel as far because you're walking up the steep side. But if you go on the less steep side, the more gradual side, by using ramps, then you actually have to walk longer, but it makes the job easier. If any of you have ever been to a mountainous region, so let's say this is a mountain, and if you try to climb straight up like this, it's very, very, very tiring. And there are no roads that are designed like this. Roads going up mountains look like this. They're called switchbacks. And by having your road switching back and forth like this, since the path is longer, we have the advantage of having a less steep climb. So using a switchback method means that you have to drive further, but with less physical effort on the vehicle because it's a more gradual increase in the slope. So that's the compromise. So next, a wheel and axle. So in a wheel and axle setup, kind of similar to a pulley, but not exactly. So here, this is your fulcrum, which is your axle. All right. Now, your load is represented by this distance here, and the force of your load is pushing down like that. Your effort is on the outside here, and your effort force is actually a little bit smaller. This is how a steering wheel works. And on big ships, for example, like when you look at old movies, like with old pirate ships, for example, the wheel was massive, right? You have a massive wheel because the larger the diameter of the wheel, the easier it is to turn. But with a large wheel, you also have to move your hands a lot. So this is an example of a wheel and axle system. So the larger this fulcrum length is, for the effort, I should say, the effort length is, the easier the job is. The larger the load length, the harder the job is. So it all depends on what you're trying to do. And gears on a bike are a prime example. Now, a bicycle is actually a compound machine because what you see here with a bike is you got a couple of things going on. First of all, we got a lever, and then we've got a wheel and axle setup. So here is the fulcrum, and here is where our gear system sets up, and of course that causes the tire to rotate. So there are actually a number of factors that we have to take in consideration. Not only the length of the lever, the relationship of the gears, but also the size of the tires compared to the size of the gears at the back, the spokes. Sorry, not the spokes, the teeth of the gears. Okay, so let's take a look. So how do we calculate mechanical advantage? Well, when in this setup here, this one is the easiest. This is medium, and this one is our hard effort. All right, so to actually calculate the mechanical advantage in this case, so the mechanical advantage, here it's the number of teeth on the output compared to the number of teeth on the input. So if you count, so this here would be your output, and this would be your input. So if you have many teeth on your output and fewer teeth on your input, the job is easier. Now in this case, if we take a look, right, mechanical advantage, it's the number of teeth on the output versus the number of teeth on the input. So this is a small number divided by a large number. So we have a very small mechanical advantage. And in this case, we actually don't get a mechanical advantage. In these cases, and in bicycles in general, they actually don't produce force advantages. What they produce are speed advantages. So a bicycle is actually geared to make you go faster, not to make the effort easier. Now, riding a bike is still easier in the sense that you can coast and you're rolling over top of surfaces. But the rate at which your foot rotates is slower than the rate in which the tire rotates. Because on a road bike, for example, if you're in the highest gear, your feet are moving relatively slow, yet your bicycle is traveling close to 40 kilometers per hour. So if your feet were to try to run on the ground at the same rate as the bike is moving, your feet would be moving very dramatically. But on a bicycle, they don't move that much at all. Now, of course, if you want to go up a hill, then this becomes a huge disadvantage. And then what you do is you adjust your bike to look more like that. And that's why we have gears on bikes, is to actually accommodate for different types of terrain. So next are the inclined plane family of machines. So stairs, ramps, wedges, and screws. So these are all examples of trying to reduce the amount of force that were required, but at the expense of increasing the distance. So let's take a look at a ramp, for example. Now, a ramp has the advantage of spreading out the effort over a larger distance. So if you have to drag something really heavy and you want to lift it straight up, this here, that represents your distance of your load. And the amount of physical effort to lift it is the force of the load. Whereas on the ramp, this is the distance of your effort. And your effort force would be required to push it up like this. So even if we didn't say have a wheel and we had to carry something slide something very, very heavy, the smaller we make this ramp, or the longer I should say we make the ramp, the easier the job becomes. And that's because the slope is less. So imagine trying to ride your bike up something like this versus riding your bike straight up a hill. Obviously impossible. But if we have a much longer ramp, the job is way easier. But you have to travel further. So the flatter the ramp is, the less effort's required, but we have to walk a little bit further. If you've ever had to move, the loading vans always have ramps for you to be able to carry up your parcel. Because carrying up a refrigerator and lifting it into the back of a van straight up is extremely physically difficult. Whereas if you use a dolly, which is a wheel and axle, so mechanical advantage there, reducing friction, plus a long ramp, a average person can actually roll a refrigerator all the way up to the top, given that the ramp is long enough and the dolly system is stable enough. So a screw is basically just an inclined plane that's wrapped around a cylinder, and it does the same thing. When we use a screw, we have to actually rotate the screw several times, which means that our hand has to rotate and cover a much larger distance than what it actually does in terms of sinking down like this. So the more threads there are on a screw, the actual easier it is. And then finally, talking about torque with levers. Now, torque is something that we actually calculate. Well, what is torque? Torque actually comes from a Latin word meaning to turn or to rotate. And the amount of torque basically is your turning power. And it's related to two things. Torque is related to how much force you apply and how big your lever is. So the combination of those two effects gives you the overall turning power. So if you have a large lever, so the D is very large, that means you're going to get a lot of torque. If you have a lot of force, you're also going to get a lot of torque. So, and if you combine those, the product of those two numbers is the equivalent of the overall torque in the system. So torque is measured in units called Newton meters. And in the old days, back before metric was used more widely, and in the auto industry, it's still used as foot pounds. So foot would be the distance part and the pound would be the force part. So it's just another way of measuring torque. So here are the rules. Counterclockwise rotations are associated with positive torques. Clockwise rotations are associated with negative torques. So for anyone who's actually ever turned a bolt, righty-tighty, lefty-loosey. So when you rotate clockwise, that tends to cause your bolts to move downward. Or think about with a water bottle. If you've got a water bottle and then here are the threads and here's the cap. So if you want the cap to come off, i.e. you want the cap to move up, you got to rotate this thing counterclockwise, right? Hence positive because it's going up. If you want to tighten the cap, right, you have to turn it clockwise and then the cap goes down, hence negative. Righty-tighty, lefty-loosey. Now, the overall torque in a system has to do the sum of all the individual torques acting on it. So let's take a look at our kind of teeter-totter system here. Here's an example. This is our fulcrum, and let's take a look at the overall torque in this system. So let's call this A, and let's call this B. So the torque is equal to the force times the distance. So on this left-hand side here, the force here wants to cause the system to rotate in this direction here, which is counterclockwise. That is your positive torque. So these things are positive torque. Now let's take a look at the other side here. So in this case, this is the distance b, and this is the FB. Notice the FB is only 2, so the FB is smaller, but the distance b is larger. So over here, our FA is larger, but our distance a is smaller. So if we take the product of the two, 5 times 1, that equals 5. And if we take 2 times 2.5, that's also equal to 5. So the two torques on the system are equal but opposite to each other. So torque A wants to make the system go counterclockwise, and torque B makes the system want to go clockwise. Now, I think, and I'm just noticing this now, the textbook looks like it got its directions wrong, because if this is the fulcrum, this is going to make it want to go opposite of a clock, which would be counterclockwise. So this is counterclockwise, and this one is supposed to be clockwise. I can't believe I've never noticed that before. Counterclockwise, clockwise. Okay. But the good thing is, when I did the math down here, I did it correctly. So T1 is this load over here, or TA, and that one is positive because it's going counterclockwise, and this one that is going clockwise is negative. And when we add those two together, we get a net torque of 0. So in general, when we're looking at a balanced system with torques in there and applying this to like your lever system, the way we think of it is that the effort torque has to be equal to the load torque, or FEDE is equal to FLDL. And then you can solve any question involving levers and to see how much distance you actually have to move or how much effort you have to make. So let's do an example. Let's do our wheelbarrow type. All right, so I'm going to draw a really simplified version of a wheelbarrow. Okay, all right, so here's my super simple version of a wheelbarrow. So this is our load here, all right? So right there, that's where our load force is focused. So what I'm going to do is I'm going to draw my F load, all right? Now the fulcrum of the system is right there, and the distance of our load, our DL, is right there. Now let's say you and I, we're using our handle. So this is the distance of our effort, and what we're trying to figure out, how much effort we will have to make. So let's say, for example, let's say the distance to our load is 0.5 meter. And let's say the distance of our effort is equal to 1.5 meters. All right. And let's say the mass of our load, is 50 kilograms. Okay. Well, if the mass of our load is 50 kilograms, we have to figure out how big our FL is. Well, our FL is equal to the weight of the load. Well, the force of the weight is the same as the force of gravity. So that's actually going to be the mass of the load times G. So that's going to be 50 times 9.8. And that's 490 newtons. All right. So 490 newtons. Let's see how much effort it would take for us to do this. Okay. Well, here's what we got. We know that the torque of the effort must equal the torque of the load. So the force of the effort times the distance of the effort is equal to the force of the load times the distance of the load. All right. Well, I want to get my effort force, so I got to divide both sides by DE. So I got my FL, my DL over my DE. Well, that's 490 times 0.5 divided by 1.5. And that works out to 163.33 repeated newtons. Well, what does that feel like? Well, that feels like 16.7 kilograms. So by doing it this way, we actually reduce our physical effort by a third. To a third. So it's 3 times easier to lift it using the wheelbarrow than it is to lift it straight up. And this will bring us to our next note called mechanical advantage.